So before I talk about RISC-V some more, I wanted to remind you that next week is the midterm. It's Thursday evening, 6 to 9, in a room which we will tell you later about. So we won't meet here in normal time on Thursday. We'll just meet for the exam. So there's no class on Thursday. Tuesday, we're going to have a review of exam topics. So make sure you come for that. Tell your friends and bring your questions. So we'll tell you what we expect to cover on the exam and kind of the highlights of what you should know on Tuesday. So it's probably a good idea to look over the material before Tuesday so you know kind of, if you have any questions, you can bring those up in class on Tuesday. So last time we started talking about the RISC-V processor. The reason we talk about processor design in this class is that it's a good example of how to do digital design. A lot of the principles that go into implementing a processor are the same principles that go into implementing other types of functionality. Right? And it's a good example for you all because you've seen some processor architecture before, perhaps in 61C or in other classes. So it's a good design example. So we use it to demonstrate a lot of the things we've been talking about so far. And also, of course, if you're taking the labs, we use it in the lab as a big design experience for you all. Plus, it's generally useful to understand how processors work. Right? So, and we use RISC-V because it's from Berkeley, and it's a particularly easy to understand processor. I realize, though, some of you have not had any processor design experience or exposure before. If you're a Berkeley student, then you had 61C, where we go into a lot of detail. In fact, a lot of what I'm going to say today, I also say in 61C. So it might be redundant, but it's probably not a bad idea to see it again. If you haven't had processor design before, then you're probably going to learn a bunch of new stuff. I put this slide together for those of you who haven't been exposed to RISC processors before to give you an idea about how the basic principles behind computing with RISC processors. So the picture at the top is kind of a cartoon version of the processor internals, where we have the instruction cache here, a data cache here. We could call it the instruction memory and the data memory for now. That's sufficient. There's a register file here, there's an ALU, and there's a program counter stuff over here. So the principle behind RISC is that the compiler is going to take your program, your C program, your Python program, your Java program, whatever it is, and convert it into a sequence of machine instructions. And these machine instructions come in various classes on RISC processors, and they have particular function. There's the load and store instructions, and these are used for moving operands or data between the data memory and the register file. No operand can be directly manipulated from memory. Okay? The processor doesn't take operands out of memory. It only takes operands for its instructions out of the register file. So we need some instructions that move the important data into the register file. And when we're done with it, we move it back to the memory. Those are the load store instructions. There's the register instructions. And these are the ones that actually do the arithmetic operations or the logical operations. They take values in the register file, they operate on them, usually in the ALU, and then send the results back into the register file. Okay, so there's that class. So those are the instructions that do the heavy lifting, do the multiplication, the addition, that kind of stuff. There's also immediate versions of these where register immediate instructions, what they do is they take one operand from the register file and another operand that's embedded right inside the instruction. Right? It's a constant value. Something that's known to the compiler to be constant, instead of putting that constant in memory, it can put that constant directly in the instruction stream, right inside the instruction. Okay. So we have some instructions that are register immediate instructions. Okay. And then we have the branch instructions, and the branch instructions are used for modifying the program flow. These are the way we implement looping and if-then-else type operations in our programs. It's conditional operation. And the conditional operation happens by modifying the value that's in the program counter. Normally, the program counter just points to the next location in the instruction memory, because the normal sequence is to just do one instruction after another. If we want to branch to somewhere else, to jump around some section of code, or to loop back to the beginning of the program or some other section of the program, we need a branch instruction to change the program counter value. And that's what the branch instructions are for. And then we have jump instructions, which are related, similar to branch instructions, except they're unconditional. They always jump when you hit one of those. And we use those for going to a function, to moving the program counter to a long distance to the beginning of a function, and then for returning back from the function to continue execution where the program was previously. Okay, so if you understand those, you pretty much have the whole story about modern day processors. Even x86 processors, which are not RISC processors, they have a bunch of instructions in these classes, and the compiler uses those instructions to compile your programs in a very similar way to the compiler uses those instructions on a RISC processor. So if you understand this, you understand a lot about what happens at the interface between hardware and software. So in order to understand how to implement a processor, which is what we're going to do today and finish up on Thursday, we're going to look at typical examples of each one of these instructions and show how we would build a data path and a controller, how we build a processing engine to execute these instructions. Because what a processor is really is just a hardware engine that executes this set of instructions. And for the RISC-V, it's a relatively compact set. Here's a complete specification for this particular RISC-V. And we have all the instructions representative of all those classes that I talked about a second ago. And we'll be going through some of these in detail. Not all of them, the ones that are typical. In your project in the lab, you'll have to implement all the instructions. So you can use the same kind of formula that we're going to talk about today to implement an instruction, and you can generalize it to other similar instructions. The instruction formats are the different ways that instructions are represented in the memory of the machine. These are, in a RISC-V, every instruction is exactly 32 bits. It makes the hardware easier to implement and simpler if all the instructions are of the same length. And depending on the type of the instruction, roughly corresponding to the classes that I talked a minute ago, there's a different representation for that. And what I mean by representation is a different interpretation of those 32 bits. Some of the fields are constant between the different instruction types. For instance, if the RS appears, it always appears in the same place on the RISC-V. Okay? If RS1 appears, it always appears the same place. Okay? The opcode is always here, so the hardware knows where to look to figure out what type of instruction it is. And there's this func field, which is also used, and that's always in the same place if it's used. It's not used for every different type of instruction. Okay? So we have a bunch of different instruction types. And when we go through the different instructions, I'll show you which instruction type is used. Right, so your goal as a designer of a processor is to figure out for each instruction when it comes in from the memory, how do you take these fields, take the instruction apart, and take these fields and figure out what to do with the information that's in those fields. Right? How do you manipulate the operands in the register file or the memory in order to achieve that function? Okay, so the way we start, and this is a little bit of a review from last time, is we look at the state that's associated with the processor. Okay, so there's a set of instructions, and then there's the state that the processor holds. This is what persists from one instruction to the next as your program is executing. And what we have is a register that holds the program counter. This is just like the normal type of registers we've been talking about. In a real machine, this would be implemented as 32 flip-flops. Right? Program counter says is the location in the instruction memory of the next instruction to execute. Some people think of it as a program pointer or an instruction pointer, points to the next instruction. We have an instruction memory that stores all the instructions to execute for some particular program. There's a data memory that's going to be used for holding data. And the data memory, if you look at it, it has a clock because it needs a clock signal in order to do a write. It's a synchronous write memory. So if you want to write a value into the data memory, you assert the write enable, meaning set that to 1. Put the address of the location of the data where it should go in the data memory on the A lines. And then the write data goes on the WD lines. This value that's on these signals will be written at that address on the rising edge of the clock. The reading for the data memory is asynchronous. It means that the reading doesn't need a clock. It's like a combinational logic circuit. That's what we mean when we say asynchronous. You change the address. If the write enable is 0, then we're assuming what we're trying to do is a read, not a write. So with this memory, you can only read or write at any point in time. So if write enable is not asserted, we do a read. If you change the address here, the read data value will change according to the value that's stored in the memory at that address. Right? So it's just a way to do a lookup. Think of it as a big kind of multiplexer where you're multiplexing out some value to the output according to the control, the address. And the other thing is the register file. And the register file is probably the most complicated thing up here because there's multiple ports. In order for our processor to be efficient and to run fast, we'd like to be able to read 2 register file values at once, and at the same time, within the same clock cycle, write a value back. Right? And you'll see this when we talk about the R-type arithmetic instructions. They'll take 2 operands from the register file, do some operation on them, and then return them back to the register file. This should all happen in one clock cycle. So we need multiple ports. We need to be able to read more than one word of data per clock cycle. The way that's achieved is to have actually 3 address ports, 2 read data ports, and 1 write data port. Right. So again, the writing is synchronous and the reading is asynchronous. So on the rising edge of the clock, if the write enable signal is asserted, then this write A3 is used to write this data value into some location. We can make it this complicated because there's only 32 locations in this memory. It's part of the definition of the RISC-V that there's only 32 registers. There's 32 32-bit wide registers. Right. So that means this address at most can be 5 bits because you can use 5 bits to specify one of 32 addresses. Right. Same thing for the reading then. If you want to read a value, put an address here and the value appears at the, put an address in A1 and the data appears at RD1, or put an address in, and put an address in A2 and a value appears at RD2. You can actually read 2 different memory locations at the same time. Okay, so we're going to put those, that's kind of the starting point for our processor, and we're going to put extra stuff around this to make it into a real processor. So it's roughly going to look like this. There's going to be a data path, and this is the place where the register file will be and where data manipulation will happen, right, under the control of a controller. Right? Here's the data memory, as I mentioned, instruction memory. The way to think about this, I always think of this kind of like a puppet and a puppeteer. So the controller is a puppeteer. It's pulling the strings. And the puppet is the data path. So the data path has the units that's needed in order to achieve the correct execution. But the controller is asserting the control lines in order to get the correct operation to happen inside the data path. So the data path is used for all the instructions. And the controller is what kind of specializes the data path for each instruction as it comes into the machine. All right, so now, if you think about building a processor based on the instruction set and based on the state elements, we have lots of choices. In fact, if you look at any instruction set architecture out in the real world, like x86, there's many different implementations of the x86. AMD has their version. Intel has a bunch of different versions. There's the low power, low speed one, low cost one. There's the high power, high fast, more expensive version. And they all differ a little bit in the way they implement the instruction set, right? And we actually have a lot of choices. Some of the choices are shown here. We have a way to do it in a single cycle. So what this means is each instruction executes in a single clock cycle. Nobody actually builds real processors this way. We teach it this way. We're going to do that today because it's a really nice and simple way to understand how to do processor design. Once we do a single cycle processor design where every instruction executes in exactly one clock cycle, then we can show how to make it a higher performance processor by pipelining it. There's multi-cycle where each instruction is broken up into a series of shorter steps and one step per clock cycle. There's pipeline version, which we'll talk about. There's superscalar, which is a very popular idea these days commercially, where there's multiple function units, and so we can execute multiple instructions at the same time. This is a way to get higher performance, to get your programs to run faster, because you're executing more than one instruction at a time, or starting more than one instruction at a time. And then some of these superscalar processors actually execute instructions out of order. So they don't have to execute strictly in program order. The hardware will reorder the instructions. And that actually can boost performance even more. We're not going to talk about most of these. We'll talk about pipelined and single cycle, because that's what you need to know for this class. If you're interested in other types of processor designs, we teach CS152, which goes into, and 252, which goes into a lot of detail about superscalar and out-of-order processors. They're very interesting machines and can get very high performance, but they're very complicated. So we don't go into it today. OK, so our first design, we're going to start out, and this will take all of today and part of Thursday, is a one instruction per cycle RISC-V machine. Right. So the idea of this is that on every tick of the clock, the computer, our processor, is going to execute one and only one instruction. Right. So the way it'll look is we have our state elements here, which is program counter, instruction memory, register file, and the data memory. There's going to be a bunch of combinational logic here. It's going to take the state at the beginning of the clock cycle. So on the clock cycle, some state, on the rising edge of the clock, some state will change here, possibly, as a result of the previous instruction. And then the next instruction will commence operating. We'll take all that input through combinational logic, and we will return some values back to the state elements. And on the rising edge of the clock, we'll change the state. So it kind of looks like a big state machine, really. We're not going to design it like we would a state machine, because it would be a very complicated state transition diagram. But we'll just kind of move through it, figure out what we need to do on a per instruction basis. So that's the idea. And there's a clock signal here that's driving these things. So keep this in mind. It's one instruction per clock cycle. So the timing is kind of going to look like this. If you think about the basic phases of instruction execution, the way it works is at the beginning of the clock cycle, we're going to let the value of the program counter move into the instruction memory and pull out the next instruction, the one that we want to execute now. Right? This value will change on the rising edge of the clock, which signals the commencing of a new instruction. That means program counter value will propagate on these wires to this address port of the memory, of the instruction memory, and an instruction will come out. And we'll split that instruction into these various fields that I showed you previously in the instruction encoding. Right. That part is, we'll decode the instruction, pulling apart the instruction, looking for the various fields. That's called the decoding. At the same time, we can do, kind of in parallel with that, certain fields of the instruction get sent to the register file to use as the addresses into the register file. And so we do register read. This propagates into the register file, and the data, the register values then come out of the register file, right, into the ALU. Usually the ALU is used. It's not used for all instructions, but for most of them. And that's called kind of an execute phase, because these operands then come into the ALU, and it can do what it needs to do. This is, again, just a combinational logic block. It might just add those two values. It might subtract, depending on what the instruction's doing. The result then will come out of the, after some delay, will come out of the output of the ALU. And if this is an instruction that uses the memory, like a store instruction, then we'll store the result into the memory at the end of the clock cycle, and get it ready to go into the memory. And then on the rising edge of the clock, it'll go into the memory, or we send the result back into the register file So then on the positive edge of the clock, the beginning of the next cycle, we'll write the result back into the register file. Okay? So that's kind of how the timing works roughly. And it all happens in one clock cycle. So we want to make sure our clock cycle has enough, the period is big enough here to accommodate the combinational logic delay through all this stuff. And this is kind of why I said, and we'll look at this more later once we're done with the details, but the reason we don't build processors this way is that it would have a very long clock cycle, low clock frequency. It wouldn't execute many instructions per second. Right? So after we do this, we'll talk about how to make it faster, and the typical technique is to use pipelining. Okay, so here we go. We're going to start figuring out the details of this data path, one instruction at a time. So we start with the add instruction. So this is a real RISC-V instruction. So it's add RD, RS1, and RS2. These are the two operands. These are addresses, or these are register identifiers. In the instruction, they're actually encoded in the machine instruction. They're encoded as 5-bit fields, saying which two register values we want to add together. And the result goes back into the RD register, which is specified in that field. You can see the opcode bit, the opcode field has this bit pattern in it, and that indicates that it's add, along with that 000 indicates that it's an add instruction. So this instruction makes two changes to the machine state. It changes the register file at the location specified by RD, right? And it also changes the program counter value. Every instruction is going to change the program counter value. Many of them will just increment the program counter by 4. Some will actually change it to a different location. The ones that change it to a dramatically different place, not just increment it, are the jump and the branch instructions. Say PC gets PC plus 4. That's because all addresses in memory are byte addresses, but instructions are 4 bytes long. So if we want to move from one instruction to the next, we have to increment by 4 bytes, or by 4. Right? So that's plus 4. OK, so we know now what we need to do, what the data path has to do, so we can figure out how to build a data path to do this. So the first part is the program counter part. So here's we said we have a program counter register. The hardware that's going to increment that by 4 on each clock cycle is simple. It's just a plus 4 unit here. This is some kind of incrementer circuit. It's a combinational logic block. We loop that around. And on every instruction, every rising edge of the clock, we just increment the program counter by 1. That works fine for add. If we had nothing but add instructions, this would work fine. We'd just move through the memory 4 bytes at a time. OK, so that's the first part. The other part is what we need in order to add the values together. So there's the instruction memory. The instruction comes out. I'm showing it go down here because it's going to go down here to the controller. Controller is going to be another combinational logic block, which is going to assert various signals in the data path, as we will see later. We also split it into these fields. This is the RS1, RS2, and the RD fields. Those are fed directly. We wire those. When we do our design, we wire those directly into the register file as shown here. And when we do that, this is the RS1 field. So the RS1 data is going to come out here, and this is the RS2 field, and the data will come out here. Then we wire that up to the ALU. And the ALU, for now, we'll assume doesn't add. We'll treat it as an adder, and then we wire its output back to the input of the register file for the write operation. So that's this write data input called data D here. Right? And then there's some control logic down here that's not doing much except one thing in this example, which is it has to assert the write enable signal for the register file. So in this instruction, we have to make sure that this signal is a 1 at the rising edge of the clock, right, at the end of this instruction cycle, so that the result gets written back into the register file. Not every instruction wants to change the register file. That's why this has to be a signal that's conditional based on which instruction we're executing. And that's why the controller makes that decision. OK, everybody got it so far? So then we're just going to repeat this for different instructions. I'll just show you the timing diagram then. Think about this. Here's a rising edge of the clock. We will see the program counter change a little bit after that. Let's say it changes to 1,000, for instance. On the next clock cycle, it would change to 1,004. Here it would be 1,008. Right? When the new program counter value comes out, then at the same time that we change the program counter value, we also compute the version for next time. So we get PC plus 4 ready. Right? So that will come out fairly early and just sit here, right, waiting for the next clock edge. Let's see, what else do we do? And then the instruction will come out of the instruction memory a little bit later, after the PC stabilizes. Right? So there's a little delay to this point. And at this point, we can recognize it's this particular instruction. Maybe add x1 plus x. I forgot I have to look something up. Hang on. Yeah, RD comes first. OK, in the notation. So what this says is this instruction, we're going to add x2 to x3 and put the result in x1. Yep.
Why is the delay different between PC plus 4 and the instruction?
Because the instruction memory, the instruction memory uses PC, not PC plus 4. This actually is a little bit misleading. This delay here is the delay through the IMEM. And this delay here is the delay through the incrementer. So this diagram assumes that there's more delay through the plus 4 operator than there is through the IMEM block.
But it doesn't have to be true.
It doesn't have to be true. It depends on how it gets implemented. In this particular case, we're using a very slow plus 4 block, which you can because you have the whole cycle to compute it. Really, this doesn't have to be ready until all the way over here, just before the setup time for the next edge. So that could be a really slow, dumb circuit. So, but this, for most important thing here is this is the delay of the IMEM block. Then we're going to have the delay for the register file block. That's here, right, from this point to this point. Both operands will come out around the same time. And then there will be a delay for the ALU to do its job, which will be here. And at this point, I think we're ready. OK, and then the value has to come back, propagate back around, and be here in time for the next rising edge of the clock, there's the sum. Oh, this is I don't know what that is. Reg 1. Oh, yeah, Reg 1. What this shows is the value inside the register file then would change at this point. The signal in the rising edge of the clock would cause this register inside the register file to change, and it would change here a little bit after the rising edge of the next clock. So that completes the execution of that instruction. It actually spills a little bit into the next cycle, but at the same time, we're starting a new instruction. OK, so that's the add. Now, if we want to implement a subtract instruction, which is one of the instructions that's very similar. In fact, the encoding is similar. The difference is it has the same opcode field, but it has this field, which is called the, I forgot what this field is called. I want to get the right name. Hang on. Func7. OK. Func7 field. Has a different Func7 field. It has an extra bit here, and that's how we know that it's a subtract. Other than that, it looks identical. Functionally, though, it's going to do this. It's going to subtract register 2 from register RS2 from RS1 rather than add. So instruction bit 30 selects between add and subtract. So the controller can know about that. And the controller can change the way the data path operates based on that bit. And the way it can do it, oops. Oh yeah, it's here. So all the instruction bits come through the controller. The controller has access to that particular bit. In this case, instruction bit 30. It can use that to signal the ALU, set the control signal into the ALU to turn it into a subtractor rather than an adder, right? And then everything will work the way it did before. Okay. So in fact, there's a whole class of these R, so-called R format instructions. They use this R format instruction format. And they all operate essentially the same way. The only difference is the function that the ALU has to perform. And their encoding on the RISC-V is very similar. The RS2, RS1, and RD fields are all the same. They all have the same opcode down here. They differ in these two fields, in the func7 field and in this func field here. Right. So it's a combination of this field, and this field tells us what type of instruction it is. And then the data path that I showed before would work just fine. The only difference now is that we have a more complicated ALU control. We need an ALU that can perform not just add and subtract, but shift left logical, or set left, what are these? Set, actually I don't remember. This is set less than, this is set less than unsigned. This is XOR, shift left logical, shift right logical, shift right arithmetic, or an and. So we build an ALU that can do any of these functions. And then we have some control signals that pick between these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it'd be 4 control signals in the ALU to allow it to perform the proper function depending on the instruction. Okay. So those are the R-type instruction, R format instructions. The next type of instructions are similar to these, except these are the immediate versions. So for instance, add immediate instruction. So this is like the other add instruction where we add 2 register values. Instead of adding 2 register values, or add this constant, so-called immediate. Immediate is some value that appears right in the instruction. Rather than putting a register specifier in the instruction, we put the actual value that we want in the instruction. We can do that in cases when the compiler has the constant. It's a compiled time constant. All right. So this uses the I-type instruction format. Here's the format. It says add I into RD, RS1, and some integer. In this case, add that integer to the value in RS1 and put the result back in RD, okay, in the register file. The immediate value is encoded inside the instruction. The instruction is 32 bits, so we don't have a 32-bit instruction immediate. We're going to have a 12-bit instruction, 12-bit immediate. But we need to turn that immediate into a 32-bit thing in order to send it into the ALU and add it all to this 32-bit value coming out of the register file. So we'll sign extend it. So that's what this means. This is what we're going to do. We're going to sign extend the immediate. Sign extending just means take the top bit and replicate it in all the bit positions. This is so that if it's a negative number, it will remain as a negative number. If you take a negative number and you sign extend that, you put the top bit, the sign bit will be a 1. It's in 2's complement. So to sign extend, we put a bunch of 1s in there. If its sign bit is a 0, we put a bunch of 0s in there, and then it remains as a positive number. Okay. So here's an example. Add the value of x1, add minus 50 the value of x1 and put it in a register x15, for instance. Okay, so this is the I-type instruction format. It has RS1, but we have no use for RS2 in this instruction. It's not used, so it's not encoded in the instruction. Instead, we use that space, along with some of the func bits, to find place for the immediate. As you will see as we go through RISC-V, if you haven't looked at it before, or any RISC processor, it's a challenging task to figure out how to encode all these different types of instructions in 32 bits. So things get kind of scrambled up a bit. But it's important to keep the instructions all the same size and to have them be as small as possible. So here's opcode. RD is in the same place. We have func3 in the same place. But now we have this 12-bit immediate field here, which can hold a 12-bit number, a signed 12-bit number. Right. So the constants that we can embed in the immediate instructions are limited in range. Right. OK, so how do we make this work in this data path? So this is the data path we ended up with for the add subtract. We can modify this. So you think about how you want to modify this. So the assumption here was that into the ALU, the two operands are just going to come out of the register file. That assumption is violated for this instruction because one of the operands will be RS1, so that one's fine. But this one now isn't necessarily going to come from the register file. We don't want to put the value into the immediate into the register file and transfer it out here. We want it to come directly from the instruction into the ALU. And the way we do that is we put a multiplexer here that can choose either the output of the register file or the immediate value, properly sign extended, and put that into the second input to the ALU. And the multiplexer will have a control signal in it, which will say where do you get it? Do you get it from the register file or do you get it from the instruction? And that control signal can be controlled by the controller because the controller logic knows what instruction we're currently executing based on the opcode field. OK, so that's what we do. Here's the change. You can look at it as I switch back and forth. So we add that multiplexer in front of the ALU. We add an immediate generator, which for now really is just a sign extender. It takes instruction bits 20 through 31 and makes an immediate that is 32 bits, right, by sign extending it. Put the multiplexer here. We added a control signal. The controller now is responsible for generating, called B-cell or B-select. It's selection for the B input to the ALU. That's what that means. If we set it to 1, then we get this output of the immediate generator rather than RS2. So something will come out here. It's important to remember the way hardware works. This field in this instruction will hold something that is interpreted as a 5-bit register specifier. And so something will come out of the register file, but it will be ignored because it's going to go to the input to the multiplexer that is not being selected. So it's kind of just comes here, and it's kind of wasted effort in some sense. We're driving those lines, we're switching those signals, but then we're going to ignore it. Right, so this is one way that power gets wasted in these circuits, because we do a lot of things in parallel and just kind of select what we want, because we want it to go fast. OK, so that's the main change. So you can see the important paths now for this instruction. They're in red. So again, we're going to do this PC plus 4 business. And as we get the new value of the PC for this instruction out, we send it to the plus 4 block. It also gets sent to the instruction memory. The instruction comes out, goes through the register file. Some part of the instruction goes to the immediate generator. That gets sign extended. That goes here. Register value comes out. This input gets selected. The ALU generates something based on, now the controller is going to tell it for this instruction to do an add. The ALU will do an add. The result will drive these wires, come back to here, and then a rising edge of the clock will change the value in the register file, and that instruction will be done. So that's the modification to the data path. I just want to say something about the I-type immediates. I mentioned this, but this box here on the bottom is showing the immediate. It's a 32-bit value. That's the value that gets sent to the ALU for this instruction. We generate that by taking these top 12 bits from the instruction, right? And then sign extending the top bit, the bit number 31 or bit number 11 of the immediate field into all this positions here. So Okay, so that was for that was modifying the data path to implement add immediate. This same technique, the same data path, once we've modified it, now works for other I-format arithmetic instructions. So this is set less than immediate, unsigned, and immediate, or immediate, XOR immediate, or immediate, shift left logical immediate, shift right logical immediate, and shift right arithmetic immediate. Okay. The only thing we need to change for all these is to change the operation that the ALU performs, and that's these control signals here. I didn't say how wide this is, but the controller can just choose the appropriate one. Yep.
So does this mean we can only implement or only use 12-bit constant values for programming?
For no, for this simple, if you want to do it in a single instruction, you can. Yeah, you only can, at most 12-bit switches plus and minus 2048.
So
but if you have a bigger immediate, there's another instruction that what you can do is load immediate into a register. I think RISC-V has load upper immediate and load lower immediate or something. You can build up immediate in a register and then use a normal R-type instruction for that. So,
okay.
Yeah. All you do is load upper immediate and then or immediate in to the bottom or something like that. Yeah. So it's a 2-instruction sequence to get it set up. This is because most constants are small in real programs. So this works most of the time. Okay. So that's the arithmetic arithmetic and logical immediate instructions. We're going to talk about implementing the load word instruction. This is the instruction that moves a word of data from the data memory into the register file. So the assembly language instructions shown here, load word into this register, a register specified by RD, some integer offset plus the value in RS1. So the way this instruction works is takes that immediate, which is that integer here, sign extends it, adds it to the value of RS1, and that becomes the address. Use that address to index into the data memory, take the result, and put it into the register file at RD. So the register holds the pointer into memory, and then we have an offset from the pointer. This is quite handy for doing like structs in C where you have multiple fields in a data structure. You may have a base pointer to the object, and you want to kind of index off that base pointer. That's what this integer gets used for. You can kind of have an offset from a base pointer. Here's an example here. That's what the syntax looks like. So it says, take the value of x2, add 8 to it, treat that as a memory address, get the value out of memory, put it into register x14. This one uses the I-type instruction format also, interestingly. Uses it in a slightly different way. You can see it has the same components. We have an immediate value, which is this offset, has the RS register, it has the RD register. So we can encode it all in the same type of instruction. The only thing that changes is the opcode is different. This is here, that means load. Right, that's the RD field. This part means load word, because in the RISC-V there's load word, there's load byte, I think there's a load half word. So there's variations. The variation is indicated by this field, the func3 field. This is the normal RS1 field. And then this is, as we had before, the immediate is stored here as a 12-bit value. In this example, it's +8. OK, so we have to change our data path to implement this instruction. This is what we had previously after we did the add immediate instruction. So now what we're going to do is use the value of the ALU in a different way, the output of the ALU in a different way. So previously, for the add immediate instruction, we took the output, the result from the ALU, the output of the ALU, and we just sent it back into the register file. Now, instead of putting that value in, we're going to treat that as a memory address. So we want to take this value here and send it into the data memory, not shown yet, or practice the data cache. and then take the result from that, the output of the data memory, and put that back into the register file, right? So we're going to need to have some multiplexing to choose where we get the data put into the register file, because now it could either come from the ALU or it could come from the data memory, right? And we need to take this signal here and split it out. So it could either go back to the register file or it could go to the address of the data memory. Okay. So that's what I'm showing here. Yeah, and it's pretty much just what I said. We take the address, the output of the ALU, it gets split. There's fan out here. It goes into the SMUX, so it could find a path back to the register file in the case of the arithmetic immediate instructions. Or it could get used here as an address in the case of the load instruction. In that case, the data comes out here and it also goes into the SMUX. And there's a new control line here, WB select, write back select. We're choosing the source for the write back. Write back means put it back into the register file. So it's either going to come from the data memory or the output of the ALU. Depending on the instruction. For this particular instruction, it's going to come from the output of the data memory. And so you can see the red lines, which are used to implement the path through this data path for the load instruction. So all this is kind of what we had before, including the PC. The difference now is the output of the ALU then goes into the register file that comes out here. The controller will select the 0 input to this multiplexer, and therefore the write back will be from the data memory into the register file. So that will implement the load word instruction, which is probably the most complicated instruction. So as I mentioned, there's other load instructions on the RISC-V. This is a table of those. There's load byte, which loads a single byte. There's a load half word, 16-bit load. Load word loads 32 bits. And then there's a load byte and load half word that treats them as unsigned, which means it doesn't do sign extension, I believe. This func3 field encodes the size and the signedness of the load data. All right, so this is how these different load instructions are distinguished. They all have the same opcode. Right. This level of detail will be important to you when you're building your processor in the lab. Right now, it's just a little detail. But you kind of see how we use the instruction encoding to distinguish between different types of instructions. Other than that, they all look the same. OK, so that was the load word. The thing that goes along with load word is store word. So this obviously is the function. This is the instruction that does the opposite. It takes values from a value from the register file and stores it out into memory. Right. So this is the assembly language here, store word, and it uses. So there's no destination register here. We have two source registers. One is used for computing the address, that's RS1, along with some immediate, which gives us an offset. And the other is RS2, and that's used for the source of the data. So we're going to take the data that's located in the register file, as indicated by RS2, put it into the memory at a location that's formed by address that's formed by taking the value of register file indicated by at a place at RS1 plus a sign extended immediate. So the instruction encoding has to be a little different than what we had for the load word, because now there's no destination register. We have two source registers, but we still need an immediate. So this is when things get a little complicated in the instruction encoding. This is the S-type instruction format. Has an opcode field in the usual place, 7 bits, it says store. Has RS1 and RS2 in the usual place. Has func3 in the usual place. And then the leftover places is where the immediate is stored. And the immediate gets split up, unfortunately. The low 5 bits of the immediate are here, and the upper, whatever it is, 7 bits are located in this position up here. Right? So the upper 7 bits of this immediate are in the same place as the upper 7 bits of the I-type immediate. Right? But the lower 7 bits, or the lower 5 bits of the immediate, instead of being here, because we need this place for RS2, we move them down over to here, this position here. So it complicates things a little bit, but we can sort that out. So this is how this particular instruction would get encoded. You would see if the immediate value is 8, the offset is 8. This is 8, and then you would have a bunch of zeros, and a bunch of zeros are stored up here in the other part of the immediate. Okay. So, like I said, we combine those two fields to form the actual 12-bit immediate, and then it gets sign extended. Okay, so this is where we were before with the after load word instruction. And now we have to modify it to accommodate the store word. So what this means is we're going to take something from the register. The difference is now something's going to come from the register file and go into the data memory. So so far we've only used the data memory for reading. Right? So we're going to activate, we're going to use wire up to the right port of the data memory. Right? And that's going to be RS2. We have to have a path from that to the data memory. And I think the rest is pretty close to what we have. Let's see. Yeah, so so write B, so the B data coming out of the register file, which is the data that corresponds to RS2, that has some fan out now. It goes into that mux as we had it before, but it also extends over here and goes into the right data port of the data memory. Right? And I think that's the only change. Oh, we've added the write signal, write enable signal to the data memory. So on this instruction, we're going to actually change the value of the data memory. Right? In fact, it's the only instruction I think that changes the value of the data memory. I think that's the only change. Let me check. Yes, that's it. Okay. So then it's shown in red. I show the path through here for this instruction. Again, we use the immediate block, get RS1 out, add that immediate in RS1. That gives us an address. RS2 also comes out. That goes to the data memory. On the rising edge of the clock, we change the value here. And there's no write back into the register file. So this is a don't care in this case. We don't care what the select mux is selecting because the register write enable signal is 0. So we can send garbage to the beginning of the input of the register file since nothing is being written. So we don't care. We'll let the controller optimize what the signal value should be because we don't care about it in this case. Okay, so that's the store word. So just a little thing about immediates again, since one of the most complicated things for RISC-V implementation is dealing with the immediates because the immediates get kind of spread out. You already saw that here, where the immediate for the I-type instruction was all concentrated here in the top 12 bits. And to turn it into a 32-bit immediate, we just had to sign extend it. But now when we introduce the possibility of having S-type instructions also, the S-type instructions split the immediate across 2 fields. As I said before, the top 5 bits in both cases are the same. Right? So those just go down into here in both cases. But we need a multiplexer somewhere in our immediate generation block, the block that's going to generate the actual immediate from the fields in the instruction. It's going to choose either between this or these bits and send that down into this position, depending on which type of instruction we have. Right? So we have this multiplexer somewhere in this immediate generator block. Okay, the last kind of major class, well, not the last, second to the last major class of instructions are the branch instructions. And these use the B-type instruction, whose format is shown here, and it has even a more complicated way of storing immediates. You can see the immediate gets split up into 4 different pieces. And then, so the hardware has to combine those together. This isn't really meant for human consumption. I mean, the machine's built to do, the compiler generates this, or the assembler generates this, and the hardware interprets it. And the only complication is for us who have to design the hardware. But you know, so it can be complicated, but the machine doesn't care. It will straighten this all out if we design it correctly. Okay, so here's a typical branch instruction, branch if equal. So what this says, if RS1 equals RS2, then set the program counter to the program counter plus some offset. This is called a PC relative branch. This is the way branches work on the RISC-V. We branch to a location relative to the current instruction, to this branch instruction. Okay, and that branch is implemented by changing the value in the register file, in the program counter to the current value plus some offset value, which is going to be stored in the immediate fields of the instruction. If you think about what we have to do here, we have to figure out a way to compare these 2 registers to see if they're equal to one another. And if they are, then change the program counter value. So we're going to have a multiplexer in front of the program counter, which will allow us to either choose PC plus 4 or choose this new value, which is computed probably using the ALU. Yes, using the ALU. We'll use the ALU to add the program counter value to the offset. Send that back to the multiplexer in front of the program counter, and then choose based on the result of this comparison. So we're going to need some hardware that can compare the 2 registers to one another. Right? Does anybody know how to do comparison? How do we compare 2 register values? If you have the 2 values on two 32-bit values. Yeah?
You do like an XOR and see if there's any ones in the...
Could do an XOR, yeah. That's generally what we do, so we do bitwise XOR, right? So this will be, you know, let's just say we're doing A equals B, so this will be A0 and B0. And this will be A1 and B1. Okay, now, XOR you want. So if they match in every position, so what XOR does, this function, so if they match, you're going to get zeros everywhere, right? And then you want to check to make sure that they're all 0. So what's that? That's effectively a big NAND, right? We wouldn't build it as one big NAND. We'll build it as a tree somehow, because this would be too slow, particularly for 32 bits. A 32-bit logic gate would be extraordinarily slow. So build some kind of tree of gates that has the same logical function as this. And I think that does it. And you can use, some people use XNORs instead, and then some other reduction. This is kind of a reduction, a NAND reduction here. Okay, that's one way to do it. There's another way to do it. Yeah. Yeah, you can subtract the 2 values, and if the result is 0, then they're the same. There have been computers that have implemented comparisons that way. But we're not going to do that here because we're going to use the ALU. We only have one subtractor in our data path so far. We could add another subtractor. Subtractors are relatively expensive. They're more expensive than these equal comparators. Or later we'll see we actually need greater than and less than comparators too. But for now, equal comparison is a lot simpler than what we could than a subtractor. And we're going to use the ALU actually for computing this offset Right. So we could put it, we're going to assume we have a dedicated branch comparator. So, all right. So what else did I want to say about this? Okay, the B format is mostly the same as S format with 2 register sources, as before, 2 register sources and a 12-bit immediate. But now the immediate represents values minus 4096 to plus 4096 in 2-byte increments. For reasons I'm not going to go into here, this branch instructions can encode offsets that are in terms of 16-bit entities, 2-byte offset increments. So the 12 bits encode even 13-bit signed byte offsets. The low bit, if they're even 2-byte offsets, the low bit is always a 0, so we don't need to store it. So even though we only have 12 bits of immediate, we're really representing 13-bit numbers. And those 13-bit numbers allow us to go minus 496 or plus 4,000, plus 4,094. Is it 4? What's 2 to the 12th? 4,096, right? Yeah, so that's right. This should be 4,000. This is 2's complement. There's one less positive number. I think it says 4,095, I think. Yeah, all right. Small detail. OK, so that's the way branches are. Let's look at actually what we need to do. This is the data path we had so far after the store word. So now we're going to make some changes. First set of changes will be around the PC here. So as I said before, we need a multiplexer here to choose the next PC value. This will be under the control of the controller, because it's going to know the result of the comparison. We have a branch comparator here. This branch comparator can compare the 2 data values coming out of the register file, send these flags, signals, down to the controller, and then the controller can set this mux accordingly. So it's now going to choose between PC plus 4 or this branch target address. The branch target address is calculated by the ALU. We're taking the immediate along with RS1, computing the offset. Oh, I'm sorry, takes PC plus the offset. Oh, I need to go back and look, sorry. Yeah, it's PC, oh, okay, yeah, that's right. RS1 and RS2 is used for the branch comparison. The ALU takes the offset plus PC value, computes the new branch target address, sends it back here, and if the branch is taken, meaning the registers were equal, then that gets loaded in the PC on the rising edge of the clock. Otherwise, we just load in PC plus 4. And we just continue executing a normal instruction sequence. So you can see things are getting a little more complicated. And then this in red now is shown what the paths are for this instruction. And the output of the register files just go into the branch comparator. They don't go any further in this case. But the ALU gets used for PC plus the immediate. And this immediate generator has to be modified a little bit in order to treat this as a 13-bit number instead of 12-bit number. What else? We added this control signal for taken or not taken. It's the PC select. And then we added the branch comparator. And I think I'm going to talk a little more about the branch comparator on the next slide. Yes, here it is. So in order to implement all the RISC-V instructions, we need not just equal compare, but we need branch. We need equal comparison. This checks if A is equal to B. it can also check if A is less than B, right? And that will come out in this signal. And then we have unsigned comparison as well, right? So there's some instructions that treat these as signed numbers and some that treat them as unsigned. Now you notice we don't explicitly generate not equal, right? Because not equal is just the complement of this. And we don't explicitly implement greater than or equal, because that's just the complement of less than. Right? So later in the semester, I think we'll talk a little more about how to do less than comparison. It's a little simpler than subtract, but again, you can think of it like subtraction. If you subtract B from A and look at the sign of the result, that will tell you whether or not B was greater than or less than A. Okay, and then some detail about the immediates. In this case, this is the B-type immediate. That was the S-type that we used for the store instruction. I said that the low bit, so when we form this immediate, we can just put a 0 in the low bit position. Treat the 12 bits from the instruction as the 12 bits 1 through bits 13, and then sign extend the rest. So these come from the various fields in the instruction. And you could see it had a fairly messy instruction encoding for the branch instruction. The immediate appears in 4 different places. There's 1 bit of the immediate, bit 13 here, 4 bits here, 6 bits here, and 1 bit up in here. And believe it or not, this actually leads to a simpler, I mean, the philosophy here is to keep the RS1, RS2 func fields always in the same place. And the consequence is then that the immediates get spread out depending on which type of instruction it is. But it's once you look at the hardware, it's relatively simple to reassemble the immediate according to which type of instruction it is. And here's kind of a summary of the different, where the immediates fields appear in the different types of instructions. And so what we need to do in order to reassemble or to make a 32-bit immediate from the various fields of the different types of instructions. Right? So if you're building hardware, you kind of have to know this in order to get all the muxing to work out properly. I won't go through all the details now. Okay, so, all right, the final instruction. I think we should have time to do at least, well, there's actually 2 more instructions, but they're both jump instructions. So the first one is the JALR, jump and link register. This uses the I format, which we've seen previously. This instruction is quite useful. It's used primarily for return from functions. Right? So inside a function, if you remember the location that the call came from, and you want to be able to jump back to that place. So that location is usually stored on the stack and then moved from the stack into a register, and then we do a jump and link register back to that location. Okay. Has this syntax, jump and link register RD RS immediate. What the semantics of this is that it writes program counter plus 4. That's the place to continue executing when we come back from the function call. Stores that to the register file. And you can say where in the register file using RD. Okay. Sets the program counter to the value of RS1 plus the offset. Oh, I'm sorry. This is not the return. I told you something wrong. This. What did I say wrong? Oh yeah, no, this is right. So what this does is if there is a, as I said, we use this for a return. So we're assuming that the address that we want to return to is stored in the register file. So this sets the program counter to a value in the register file. And we can have some offset off of that because we have an immediate, okay? This uses the same I-type format as the arithmetic and the loads, okay? So in this case, the offset is stored there. We have the value here, the RS1, which we need to get and to put it into the PC. We also need to store the value from the program counter plus 4 into the register file. Okay, so that's going to make a change. And I think we have another change here for the program counter can actually come from a third place now. No, we did. We compute. I think this is the same that we use for the branch. We'll take a look and see. I can't remember the details now. Yeah, so here's what we had for branches. And now we're going to change it. Yeah, so the program counter part doesn't change. We add just one wire. We add another input to the write-back multiplexer so that we can write into the register file the value of PC plus 4. So we take that line here, add this extra input into the multiplexer so that we can write into the register file that value, the program counter value. Right? Right. So that's that. And then the final instruction, which will be the end of it, is the jump and link instruction. And this is what we use for function calls usually. It saves the program counter plus 4 into the register file. This will be the return address, kind of used in a pair with the previous instruction. Okay. And it sets the program counter to program counter plus offset. So this is a PC relative jump, similar to what we had in the case of the branches. But it's unconditional, right? And it's like a branch, but it's unconditional. Also, we need to remember, store in the register file, PC plus 4. All right. So this means we want, in this case, we want to be able to jump a long way. Right? So we want it as big and immediate as possible. So a lot of the instruction bits, this uses a J-type instruction, which reserves a lot of the bits in the instruction for the immediate. In this case, we have 20 bits, 21 bits. Well, there's effectively 21 bits of immediate, but the low bit is always a 0 because, again, we're jumping to increments of 2 bytes. So we can target anywhere between plus and minus 2 to the 19 different locations, okay, which is this number of instructions. This is needed because programs can get very large, right? And the code for the functions may be a long way away from where you're executing. If your program is bigger than this range, you could jump to a jump if you had to, right? Okay, so what do we need to do in this case? We already had the logic for storing the PC plus 4 into the register file, so we don't need to add that. I think we already had PC plus offsets. Yes, we did. Okay, so all we do is add some controller logic to control the various muxes to get this set of operations to occur. In this case, the big change is we have this mux where we choose PC plus 4, put that into a register file as we did previously, and then program counter gets this upper input, which is the output of the ALU, and the ALU is going to, this multiplexer gets a PC value, and we add the offset to it here, and that goes back around into the PC. right? And so that's it. Once we have that instruction, then I think we have everything. And this is the completed data path here with all the control signals. So in class, we're not going to add any more complexity to this. There's a few more instructions that you'll have to worry about when you implement it in the lab for the project. But you know, this is pretty close to what you will end up implementing. And then what remains in the processor design then is really worrying about this part down here. Right. Now, the logic down in the controller. And that's the part that takes the instruction and the various other signals that come into it and generate all these control signals that go up to control the type of immediate, all the muxes, the write enable signals for the memories, all that kind of stuff that comes from the controller. So, you know, it's kind of like a table lookup operation, really. Based on what type of instruction and some other input, you can generate what the control signals should be, right? So in Verilog, this actually works out very nicely as a big case statement. Right. So you kind of case off the opcode. And this is a way to build this kind of decoder type thing, instruction decoder, where, for instance, up here you can specify default values for the control signals. And then depending on what instruction you're in and perhaps some other input into the controller, you can set the other control signals accordingly. So you have to just make sure that every control signal gets defined to the correct value according to which instruction. And it's not just the instruction, there's other things. Like if it's a branch instruction, you also need the output from the branch comparator in order to set the muxes appropriately. But again, it's a big kind of case statement is a nice way to implement it. And you'll get some combinational logic block, which is really messy, but you don't care. The tools will optimize it pretty well. Okay? So that's it for now. That tells you how to implement a RISC processor. I hope you got all that. That's a single cycle RISC processor. Next time, we'll talk about processor pipelining, how we can make this a higher performance processor for very little cost and without much effort. Okay, so that'll be coming up on Thursday. Okay, so see you later.